Again, good morning and welcome. Today we are starting actually brand new topic. This is exam 4 basically material. Exam 4 material cover basically some stuff related to geology and mainly astronomy. And this is the last part of this course. So this is the end of it. So basically, as I was saying before the recording, we have next week, which is going to be a full-fledged basically week in terms of instruction. And then the week after is going to be half basically material. And then after that, we're going to start our exam review for exam 4, and then actual exam 4, and the review for the final and the actual final on June 8th. And that is the end of everything in here in terms of class, in terms of the content, which was a big journey. We started way back on February 16th, I believe. No, February 16th was the first day when we met. And we're going to end it on June 8th, covering materials related to physical science, basically in general, namely the physics component of it, plus the chemistry component of it, plus the geology component of it, which we're starting today, with the astronomy component of it. And that's basically the entire course for you guys. Okay. So because the content is quite a bit today, so I'm going to start sharing with you the screen immediately. Share, where is the, oh man, let me show more windows. Let's see, what is it? That, there it is, all the way to the bottom. Okay, again, chapter 22. Deals with, let me move this a little bit closer in here so that you can see where we are. Let me move this in here too. If there is anybody who write a comment or something in the chat, so they can pick it up. Anyway, so again, shaping Earth's surface. So there are two topics in here. We're going to talk about how the surface of the Earth. By the way, all of these things that we do for the Earth also for a lot of degree apply to other planets. Obviously, we have to examine other planets to see what they have. For example, there is no surface water that we know of on Venus or Mars, or even for that matter, Mercury. So we don't really know a lot of this. Am I sharing the screen or is there something wrong in here?
Looks good to me.
Yeah. Okay. I think those are things that I need to fix, Corin. Okay. Please remind me again if you don't see them. Okay. If you see them still with those things. Okay. So anyway. Okay. Wait a minute. Maybe you're right on that. Yeah. I'll examine that. Okay. To go through these things to make sure that we have. So again, in terms of the, like I said, I mean, a lot of these things that do apply to the Earth apply to some of these planets in there. And, oh, I see what you're saying, Corin. I think you're right. I think we need to readjust this thing down the road. I think probably the plan may be a little bit pushed back, okay? I think I put things out of order, but then I'm going to fix them hopefully by next week, okay? So anyway, so in terms of water surface, so basically in terms of a water cycle, Earth has this feature in it. Some of the things that do apply to Earth, for example, in terms of the wind and other parameters, for example, they do apply to other planets. So we learn a lot from the example of the Earth. So when we hit the topic of the solar system later on, and actually even for exoplanets, we'll probably expand some of the things that we know about them from the Earth. Anyway, so the first thing that affects the surface of the Earth is the water, and be it basically standing water, whether in the oceans or in lakes or running water in streams and rivers, or even the cycle of the water in general, like rain and precipitation in general in the form of snow, or even in the form of ice, basically, whether in terms of snow or other forms of water. So it shapes a lot the Earth. Then at the end, we're going to probably talk about the effects of the air on the surface of the Earth. Then we're going to look into the history of the Earth, and we're going to use basically two methods of keeping track of the age of the Earth. First one is relative dating, and when we say relative dating, basically is that how is this layer or how this part of the surface of the Earth compares to another one. So that is what relative mean, in relation to one another. And that gives us a visual, and that's actually a very powerful technique of also dating the surface of the Earth and basically learning about the history of the Earth based on that. And also that applies to a lot of other surfaces, not just in the case of the Earth. The Earth is it's close to us, so we can touch it all the time, and we have other techniques to it. The other method, as a matter of fact, is actually radiometric dating. You take a sample, you put it into of the Earth, a rock, for example, and you take it to the laboratory actually and see its composition. What does it have inside? If you know, for example, that there are some isotopes from different materials that have specific half-lives, okay? And if you measure how much of those isotopes exist in that rock versus how much, so you have in this case what is known as a parent and a daughter. The parent in this case is the isotope that gave rise to the other elements. And if you find the ratio of the two, then you can tell how old that rock is or how old that specimen is. Now, depending on the type of agent that you would want to, now you have to really target the elements that you would want to examine. If you're looking at a big scale age, for example, over billions of years, you really have to look for materials that have that much half-life. Like, for example, uranium-238, which has a half-life of about 4.5 billion years, okay? Meaning that in 4.5 billion years, whatever I start with from uranium-238 is cut in half, okay? The other ones are the daughters, basically, because the process of radioactivity goes through several stages. So the byproducts of this process. And then the same thing, for example, if you're looking for a few 100 million years, then probably uranium-235 would be a better candidate for you, because uranium-238 will give you a very wide range with a big margin of error that you wouldn't tell what happened in this transition between this few million years and this few million years. So you need a more precise equipment for that. If you're looking for something of organic nature, for example, a few thousand years, then in this case, carbon-14 will be your best bet. So again, this is something that teaches us in terms of what's going on in terms of the surface of the Earth and what's happening on it. So the water on the surface of the Earth is mainly in the oceans, okay? More than 97% of it is in the oceans. And the remaining less than 3% is actually the other forms of water, especially the ice caps, which is a little over 2%. So that's where the bulk of the fresh water is, okay? And then you have the groundwater, the surface water, and the soil moisture, which represent about less than 1% altogether. So that is the fresh water, if you wish, versus the saline water that has high concentration of salt in it, which is mainly in the oceans. So this is basically how the water is. Water goes through a cycle, and the cycle goes basically through these steps: evaporation, and then evaporation is due to the heat that is on the surface of mainly the oceans. And then you have precipitation due mainly to gravity, condensation, and then followed by precipitation. The precipitation at the end goes either in the form of rain or in the form of snow, goes through runoffs back to the oceans. And sometimes what you have in this case, you have evaporation right from those stages. So the evaporation does not necessarily happen from the oceans, although it's mainly the oceans that are cause of that, okay? In a rainforest, for example, it's actually a different process that gives you those evaporations, but it's still evaporation nonetheless. So you have 4 stages, basically: evaporation, precipitation, and then runoffs, and back into evaporation. Did I say 4? Yeah, it's actually 3 of them, okay? So that is, and the runoff can be on the surface or below the surface, okay, of the soil. So this is basically, okay. Oh, the infiltration is the 4th stage, okay? And this is actually parallel with the runoff. So that is the 4 stages. So evaporation, precipitation, Infiltration and runoff both brings the water back into to recycle it. So this is actually a full cycle process. So in this case, the water that goes from it forms a complete cycle. Not all water does that, though. Some of the water goes into the surface, for example, of the into an ice precipitation in the form of a snow can sometimes stay there. Okay, takes a long time for it to cycle. If you want to think about it, there it takes geological time. But on a regular basis, this is basically the process through which this whole thing, this journey of the water, goes. Again, water can flow in streams, rivers, and also in groundwater. Okay, but it can also be frozen in ice caps and glaciers. That's the point I was trying to make. Okay, so it's not always, the journey is not always direct way to through this process. Okay. Earth's natural supply of fresh water comes mainly from where? From the rain and snow, not glaciers. So this is basically where our main fresh water, where we get it from. So factors that influence storage of and movement of water is porosity, which is the how much basically space is there for the water to go and sit. So it's actually the space in the soil, sediment, or rocks where the water basically can gather. So it's the amount of open space that is underground. So that is basically what influences the movement of groundwater. Greater porosity equals more potential to store greater amounts of groundwater. Particle size, shape, and influence of porosity. Soil, of course, will influence, all kinds of things will influence the porosity. In addition to that, you have the permeability. The permeability is the degree to which groundwater can flow through a porous material. Higher permeability, greater potential for fluid flow. It's like the conductivity when we did electricity, really. So the permeability is how much it will allow for the flow of water. For example, clay is not really good permeable material versus, for example, the sand, which let the water seep through it versus the clay. So sediment packing and connectedness of pores influence permeability. Hydraulic conductivity, a measure of permeability, tells us the degree to which the material can transmit water. So a lot of this terminology is used in here. So water beneath the ground exists as groundwater and soil moisture. Groundwater in the saturated zone, water has filled the porous spaces. So when it's saturated, all of the space that is available has been basically filled. Moisture above that is actually in the saturated is called an unsaturated zone. So the limit between them is what we call the water table. Okay. The depth of the water table varies with precipitation, of course. The more rain you have, the more accumulation of water is going to go there. And climate, 0 in marshes and swamps, because then it's all of the water is actually above the surface in this case. But it's greater in the desert because then you have a lot of it going underneath and sitting in there. Perennial lakes and streams, the water table, so it's going to add to it, okay? The water table tends to rise and fall with the surface topology, with the mountains, basically the whatever is underneath here. So if there is an impermeable surface underneath, so in this case, no matter how, it follows the shape of that region below it. Aquifers are reservoirs of groundwater. Aquifers are vital, of course, as a source of fresh water. Aquifers generally have high porosity and high permeability. And aquifers underlie the land surface in many areas. It is important to keep this vital source, of course, as a source of fresh water, and keep it also contaminant free. A perched water table, like in this case and here, this is the perched water table in this case, because you have a low permeability layer. So you have in this case the water in here. However, spring starts to form in here and seep the water from this if you wish, pocket of water all the way to the main water table. And in this case, the springs can tell us a lot about what's going on in terms of the surface in here. Another factor that influences the flow of water groundwater is the hydraulic head, which is really the gradient between this level. So if there is like a slope in this case, so that slope or that difference in height will tell us how. Of course, the greater the difference in height, the faster the flow of the fluid is. If the slope is less, then in this case the flow is going to be less. As a matter of fact, this is Darcy's formula that gives you the ground water flow rate, okay, which is the hydraulic conductivity, how good conductive the material is, times, or namely the permeability in this case, times the cross-sectional. The bigger the area, the more flow is going to go through it. The smaller the area, the less flow is going to go through it. And the hydraulic gradient, which is really how the difference in height between the different levels. So that is basically how you're going to find how fast the flow is, okay? Flowing groundwater can alter and change the features of the landscape. One of them is the land subsidence. Basically, the land subsides because of the fact you're removing water from underneath of it. So in this case, the surface of the land starts to go down and down. Also, it can form caves and caverns. And caverns are really big caves. That's the difference between them. Or sinkholes, which are open to the sky. Okay. So here is the San Joaquin Valley, or the Central Valley here in California. From 1925, this is where actually the ground level was. And it's been going down ever since that time because of the irrigation, taking water from the ground. And in doing so, basically, the land is readjusting itself because there is no support underneath. So it's going down and down. And this is in 1997. Look at the height of this versus a person standing on it next to it. So this person is about 1.5 meters. So you're looking at 3 meters, about 6 meters, about 9 meters down. It's almost 30 feet, basically, went down. And from 1927 to 1977, that's about 50 years. So this is big. This is a lot, okay? So as water is pumped out of the ground, the fine grained clay particles become compacted, causing the land surface to lower. So the dissolving action of groundwater eats away at rock limestone in particular, because basically rainwater reacts with carbon dioxide in the air and becomes acidic, and because the acids will dissolve basically limestone in this case, and when it does, it starts forming these formations in here, which are these small caves, and then followed by this large caverns in this case here. So that's basically how the process is. So the rain in this case becomes acidic. As it becomes acidic, it eats from the limestone, which is mainly really based off of calcium and other minerals. So sinkholes are funnel-shaped cavities in the ground that are open to the sky, and they are formed in a similar process actually as the caves and caverns. And there also can be formed with the withdrawal of groundwater. Surface water includes streams. That's another process of actually affecting the surface of the earth, is through surface water via streams, rivers, lakes, and reservoirs. So that's basically surface water. Infiltration of water is controlled by the intensity and duration of the precipitation. The more rain you have, the more streams you're going to have, and the more rivers you're going to have, and the more levels of the lakes and reservoirs grow. And with the flow of water, of course, the surface of the earth is going to be impacted, and that is going to basically carry with it sediments, is going to carry with it actually rocks, depending on how turbulent the stream is. If it's laminar, it's going to carry small rocks. If it's turbulent, it can carry actually big rocks and boulders, and in doing so, it's going to change the shape of the surface of the earth. So again, running water shapes Earth's surface in two opposing ways, actually. First of all, it carves out the landscape, basically cut through it. And then in addition to that, it deposits materials, and both of them are antagonists to one another. So basically it's chewing away from it, but also it can deposit materials on it, especially when you go to the deltas. Like for example, near, I don't know, Mississippi Delta. Stream flow geometry. So that's basically, there are two factors: the gradient or the slope, which is always important, and the discharge volume of water past a given point, and the geometry you have the shape of and the size of it. So that's okay. So the flow, average flow again is the discharge cross times the cross-sectional area. And it's a similar formula, basically, how much is the speed times the area. And here is an important property of this flow in this case. Obviously, near the surface of the stream, near the ground, basically, where the water is in contact with the surface, the flow in this case is slow, and that is because of the friction. But as you move away from it, the flow is faster and faster. As a matter of fact, in the big depth in here, the flow is going to be the greatest. From that, you can clearly see that in this case, the flow is going to be fastest around the further away from the curvature. This river is curving this way, so in this case, the stream is faster here, whereas in this case, it's curving in the opposite direction, so it's faster in the opposite direction, because it's chewing from this side. So in doing so, it's much deeper on this side than on the other side, which is closer in contact to the surface of the ground. There are the main streams in the United States, or rivers. Basically, you have the Mississippi River, and with its tributaries, in this case, the Missouri, the Ohio, the Arkansas, and the Red River. You have the Rio Grande by itself, and all of them, they're coming from the Continental Divide. That is actually where the main source of this rivers are. Obviously, the Ohio and the Mississippi is coming all the way from the northern lakes in Minnesota, and they all meet together in this delta in here. This is the eastern, basically, or the Atlantic side. What is it called? The Atlantic drainage. On the other side, you have the Pacific drainage. The Pacific drainage, you have the Colorado River, which is a big river that Southern California depends on a lot. We get about 30% of our fresh water from it, so it's a very important source of water. Also, we get our water from the Sacramento River too, which is makes up probably the bulk of the water that we get into Southern California via canals that are brought in here to Southern California. And also, there are other rivers that go all the way to the northwest, in this case, mainly Oregon and Washington. So again, Snake, Columbia rivers, they all meet together in that. So again, these are the main, of course you have so small, like the Hudson and the Delaware in the east. So again, flowing surface water sculpts and shapes the Earth's surface, and that is due to erosion. Erosion sculpting action carves the landscape, or deposition, that's the opposite to it, which shapes the landscape in the form of sediment deposits. The flow, as I mentioned before, there are two types. There is a laminar flow, which is a linear flow, and there is a nonlinear flow, which is a turbulent flow. Turbulent flow can carry with it big boulders, whereas a laminar flow cannot do that. It carries with it small rocks or small tiny pebbles, if you wish. Okay. Streams transport a great amount of sediment from one location to another. Laminar flow can lift and carry only the very smallest and lightest particles. Turbulent flow can move and carry a range of particle sizes. It moves particle downstreams mainly by lifting them into the flow and basically, or rolling them or sliding them. The smaller, finer particles remain suspended in the basically the murky water. Again, there are three main ways for basically affecting the surface, either through chemical weathering. The streams of water carries with it and dissolves the rocks. The hydraulic action, which is in this case erosion and movement of great quantities of sediment and rocks, and abrasion in this case, which is the friction of the rock with the surface of the bed, in this case of the river or the stream. So stream or loosely consolidated particles are lifted by abrasion and dissolution, and stronger currents lift particles more effectively. Stronger currents have higher energy, of course, because they have more kinetic energy, lift and surf for more and bigger particles, and turbulent versus laminar. Laminar is linear. You have this V shape in here near usually the mountains where there is a big gradient in the surface of the water, so that will cause much faster flow in this case and give you this V-shaped valleys. And downstream, in this case, you will have more of a uniform or floodplains in this case, and the rivers can form in this case deposits, and this deposit become natural levees, okay, for the water not to flow anymore. Again, the deltas are where the water stream meets a standing body of water. So in this case, it comes to a slows down big time and brings with it the deposits in here, okay? And usually it has this fan-shaped form. Here is an example of a delta in this case. Glaciers are powerful agents or also of erosion. A glacier is like a plow as it scrapes and plucks up rocks and sediments. So that's because there's a big amount of ice that is usually sitting on top of the rock. And the more you have it, the more basically it's susceptible to move. And with it, it's going to also carry with it the deposit with it materials too. So there are two types. They are alpine near the mountains and the continental in the middle of the ocean, in the middle of the lands. Okay. So you need actually a great weight of a lot of snow, and it's going to move under its own weight because of gravity. Again, when a glacier ice exceeds 50 meters, the pressure on the overlaying becomes so much that then you have a non-linear, you have a non-elastic flow in this case. What I mean by plastic in this case is that it's deformation. It's going to change, it's going to move away. So it can melt also because of the heat too. So how is the glaciers work? You have always an additive action in this case in the form of snow. So that adds more to the ice on it. But the sublimation, which is a transformation of the solid ice directly into air, that is one way of losing basically some of its mass, or it could melt away, okay? So, and that is actually through the motion in here. So that is basically how the cycle, if you wish, of the ice in this case is, or glacier is forming. Again, I mentioned the fact that these are actually alpine glaciers. Again, it can carry with it also a lot of rocks and a lot of deposits and a lot of stuff also similar to the regular flow. Air has also similar effects. Air, if it's basically not to the same extent as water flow, but it's going to have a lot of effect if it's too fast or strong winds in the regions where there is strong winds and sparse vegetations and the particles are small, like the desert, for example. Okay. Geological time, again, I mentioned in the introduction the fact that there are two methods of dating, okay? First of all, let's look at the Earth overall. It's been going on for about 4.5 billion years, and if the sun goes in the same rate, it's going to also continue for another 4.5 billion. So the Earth right now is just in its middle of the age of the solar system, which puts it right midway where it's the whole solar system is. In about 4.5 billion years, maybe a little before that, it may not be in the same form that we see it today. Anyway, the Earth form, let's say, for example, compare it to 1 year. Let's say, for example, the entire Earth is formed in 1 year. So on January 1st, it was formed. The oldest rocks that were recorded actually, and that were dated in here, are February 26th. So we have no clue what happened between January 1st to February 26th. Bacterial life showed up around March 23rd. So we're still in basically the end of the winter. The first 3 months, the Earth had life in it. And this is actually a very important fact in here, because when life, it seems like it can happen, it does, at least what we know from the Earth. If this is the case, then we probably need to test this hypothesis with other planets. That's one of the things that is going on right now with Mars, the Perseverance project, and also other projects before it, to see if the same thing can be said about Mars too. When the conditions were ripe for life, did life also exist on that planet? That's really how the question that we're asking for. Because if Earth is 1 year old, I know it's 4.5 billion, the first, basically, in 25% of its life, of its existence, it showed life on it. For the next 3/4 of its life, it still shows basically biological life on it. So that's basically the point in it. Dinosaurs appeared from December 14th to December 26th. So that lasted a long time compared to the Homo sapiens, which appeared only about 10 minutes ago. So life, for the most part, at least compared to between the dinosaurs and the Homo sapiens, let alone modern humans, human society, which appeared in the last minute. Okay, so that is really something to ponder about, at least to see exactly how things are in scale. I mean, we think that we've been living forever, but it's not true. I mean, we've been in here on Earth for about a minute compared to everything else. Again, I mentioned the fact that relative dating is one way for us to tell the age of the rocks and the surface of the Earth. And as I said, is because comparing two different surfaces to one another. So the other method is radiometric dating. And radiometric dating is a little bit more accurate in the sense it gives you precise measurements in the laboratory. So here are the rules for relative dating. Relative dating, first of all, one of its rules is the original horizontality, meaning that new layers of sediments are horizontally laid, okay, down one on top of the other. So this is rule number one, because of the deposits. One comes on top, so the top one is usually younger than the one in the bottom, okay? Superposition. In undeformed sequence of rock, top layers are younger than the bottom ones. And cross-cutting, a fault, so if you're looking at different layers in here, and you see cross-cutting through them for one process or the other. So in this case, the cross-cut must have happened later in time than before. So layers, the top layer is younger, whatever causes them cut across them, that must have happened later, I mean, younger. Inclusion. If you look at a rock, for example, and there is a small portion of it that has a different structure, different composition, then you know that what is included in this case must be older than the outer shell. The other one must have gathered later in time. Lateral continuity allows us to date separate rock outcomes from similar characteristics. You have one here and one there, so in this case there is a discontinuity. So that discontinuity must have happened later, because if I look at this layers in here, I see their counterparts in the other layer structure, but I see there is a shift in here. So that shift must have happened later, okay? And then the effects of life in this case. Life happens in a certain sequence, okay? Like, for example, trees, they grow from the inside out in terms of trunks. So if I see that, I know the inner ones must be younger than the outer ones, and basically that's how I can tell the age of whatever I'm looking at. So this is relative dating. This is basically comparing things to one another. Obviously, the deformations or the inconformities can happen with different effects in this case. Again, radiometric dating relies on specific properties of different materials. As I said before, you have uranium-238 versus lead-206. So the parent is uranium-238, the daughter in this case is lead-206. And if I look at the comparison of the two, let's say, for example, I have a sample that is 1 kilogram, weighs 1 kilogram. Half of that is uranium-238 and the other half is lead-206. I know this rock must be 4.5 billion years old. That is basically because lead-206 can only be formed from uranium-238, and this must have taken 4.5 billion years to do that. If I find a rock, for example, where actually mostly uranium-238 and very little lead, then this rock must be young. If it's on the other side, most of the rock is lead-206, and only very little is left uranium-238, then in this case, I know that this rock is much older than 4.5 billion years old. Okay, This was a major discovery, because up until the 19th, toward the end of the 19th century, we didn't know, before discovering radioactivity and the properties of radioactive materials and things like that, we had some understanding that Earth was old. We know that Earth was old. How old was Earth? The best estimates give us a few million years old, based on, again, what we know about the rocks, what we know, for example, about the relative dating and things like that. So, and we know the sun has been shining for that long at least. So again, we had an estimate for the life, or at least the age of the solar system, about few, maybe several dozens of million years, maybe 100 million years at best. And that was the end of it. Until we discovered this techniques of radiometric dating, then we have a very better, much better, if you wish, knowledge of how old this the solar system is. As a matter of fact, the meteorites that come to the Earth, which are completely not affected by the activity of the inside of the Earth, those, I mean, the inside of all of the planets, because they have formed exactly the same time when the planets were formed, but they didn't go any kind of heating or any kind of changes. So those meteorites provide a very valuable, basically, a piece of scientific equipment, scientific, basically, discovery, so that we can tell about the age of the solar system. So that's why people are always in the hunt for those, trying to see them, because you take a rock like that one, and you put it in the laboratory, and you analyze it, and then you will know more about the early solar system. So that is very important piece of study. Now, as I said in the intro, if you are not really interested in billions of years, but you really want to see what happened, for example, between this era and that era, and they are a few 100 million years, and in this case, it's not really practical to use uranium-238. You need probably something else, like, for example, uranium-235. Okay. Uranium-235 will be better, because in this case, its half-life is 700 million years. Again, its byproduct is lead-207, so you have to compare the two. Obviously, uranium-238 is not everywhere in the on the crusts of the Earth, so you really, sometimes you don't have that luxury, so you have to use a different material, for example, like potassium in this case, which transforms to argon, and its half-life is 1.3 billion years. So that's still a good number to measure with, because if you start with 1 kilogram of potassium and you wait 4.5 billion years, that 1 kilogram of potassium probably will become maybe 200 grams. So you still have some of it in there left. So the parent still did not go completely out. So this is why it's important to have it in here. Carbon-14, on the other hand, is 5,700 years. So it's not going to be practical for millions of years or billions of years. So carbon-14, for example, is dating stuff that is few thousand years old, for example, from the Egyptian era to whatever the, I mean, the modern history, basically, of humans. So that is good for it. Okay. You look at the entire planet now, based on what we know from, especially the radiometric dating. This is basically the age of the different, basically, eons, first of all, and the eras on the Earth. This, on this side in here, it's millions of years before us. So now it's 4.5 billion before, and this is the Precambrian time. At that point, the Earth was not really good for life the way we know it today. There was no oxygen. Okay, so animals could not survive under those conditions. So it was the Cambrian era, and the first plant fossils that started to form oxygen, and that's only 500 million years ago. So when we look today, for example, on Venus, and we see that it's really a nightmare in terms of its conditions, the Earth was not always like this. The Earth actually went through a lot of evolution to become suitable to the life that we know it today. Okay? Again, these are the different, in this case, eras, and then including about a few 100 million years ago, 248 million, 244 million, over 100 million, basically. Oh, how much is it? It's actually more than that, where the age of the dinosaurs was. and then to modern era, including all the way to the last part of this era now. So again, the Precambrian ranges about 4.5 billion years to about 500 million years, or 543 million years ago, and that is 90% of the history of the Earth. Only the 10% is what looks familiar to us. Okay. So there was considerable volcanic activity, and that's in the early on, especially in the early life of the Earth. There was actually heavy bombardment time where there was a lot of meteorites falling on the Earth. Okay, and they brought, among other things, water with them. So it's actually good that they happened. And the primitive atmosphere and oceans that formed when the Earth starts to cool down, and the beginning of the lithosphere and the formation of basically a movement. So the Precambrian, most common are material deposited by algae and plants fossil in the middle of the Precambrian era. So that's at that time we started to form basically plants in it. Okay, so the first atmosphere, primarily hydrogen and helium, like the sun right now is primarily hydrogen and helium. Jupiter primarily, and that's actually all of the planets at that time. The only trouble with it is the big planets like Jupiter, Saturn, and Uranus, and Neptune, they're too massive. They retain their hydrogen and helium. The Earth, on the opposite, and the other smaller planets, they're smaller, so they lost most of their hydrogen and helium. However, some of that hydrogen combined with the oxygen that formed after that, but especially through the outgassing, through the volcanic activity on the Earth, and that made the atmosphere, in this case for the Earth, was rich in carbon dioxide and water, but there was no oxygen. Water condensed to form oceans because of the cooling of the temperature of the surface of the Earth. And the third atmosphere, which is the third stage, is the removal of carbon dioxide, and basically it's deposited into rocks, right? Rocks today hold the bulk content of carbon dioxide. Nitrogen increased in the atmosphere, and oxygen, especially through the photosynthesis, starts to form. And then later on, the development of the ozone, which is right now necessary for the life to exist on Earth, because it absorbs ultraviolet radiation and converts back into oxygen in a cycle, in a process that involves the creation of the ozone through the help of nitrogen as a catalyst. Again, we're moving in the eras, and here the Paleozoic Era. It's about 300 million years ago. Again, it has several periods in it. Okay. Periods are characterized by changes in life forms. So each period has changed in life forms and tectonics, also the movements of the different surface of the plates of the Earth. Okay, Corin, I'm going back to your point very, very much. Okay, so we really need to make that correction. Thank you very much. Okay, I just remembered because this is very important. The tectonic and plate tectonics are very important. So we're not going to skip those two items in here. So in sea level rise and fall of sea levels, because they help us understand how the early Earth was too. So Capric Explosion, which that is basically when life seems to have flourished every which way, okay? But it's also characterized with several extension too, this period too. So abundant and diverse marine life and the formation of the first species with vertebrates in them, and the surge in rate of extensions. Many land masses journey to become southern Gondwana land, okay? And then you have the northern one. But in the middle, basically, of the Earth, there was no land in it, which means that there was no heat for it to trap heat. So the temperature was very, very low. So this is basically, and the surface of the water starts to shrink because of the fact that there was a lot of ice forming in here in the southern area of the South Pole and North Pole. So this is North America, South America, and this is the Gondwana land, which is the rest of the plates. So this is, again, another era in here, which is from 417 to 350 million years. That is how the plates were moving. And then as the plates moved, then they became part of the equator, the temperature starts to change, and this change in temperature starts to warm the planet a little, okay? And different forms of planets, the animals formed. And Paleozoic, again, era, we're still in the Permian period, which is 290 million to 248 million. And in this case, vertebrates continue to diversify, and ancestral links to mammals and reptiles. And 95% of them, so this is also a Permian extension. So again, we talked about the surge of extinctions. 95% of all marine species basically went extinct. 70% of land species went extinct. Okay. The Mesozoic era, which is from 180 million, which is the entire thing is about 248 million to 65 million years ago. And this is divided into three periods, basically the Triassic, the Jurassic, and the Cretaceous. And it's all called the age of the reptiles, and that's the age of the dinosaurs, basically. Okay. So again, begins in much the same. The land has above sea level, which allowed for this diversity of life to expand all the corners of the different continents. And we have the survivors of this one are the pines and redwoods. Okay. Again, it's dominated by dinosaurs, and one group of those reptiles, of course, led to the evolution of birds. But then it ended abruptly around 65 million years ago. There are a couple of competing theories for it. One of them is actually a comet or asteroid that probably most likely happened in the Yucatan in Mexico. And that caused a massive, basically, extinction because of the fact that the temperature went down big time. Or extensive volcanism also, or both of them. Could be both of these two processes led to that, okay? Okay, and then the modern era, which is from 65 million to present, and this is called the age of the mammals. And this is basically when the breakup of the Pangaeas, in this case, into different continents. And you have, it's divided into two main periods, the tertiary and quaternary. And we are in the last age of that era. Okay, so that is the formation of the Himalayas and the different mountains in Europe. And of course, the climate cooled, and humans evolved at the end of this era. Anyway, so this is in a nutshell this chapter, and I'm sorry that we went a little bit out of order on it, because we need to come back to the basically how the Earth is formed, and the different layers of the Earth and the different layers of the structure of the Earth. So hopefully I'm going to readjust the chapters again a little bit. By Tuesday, issue this order, which pushes a little bit the content to the edge in terms of the final.
So,
good?
Do we post anything for today? Okay.
No, not any questions. Okay.
Okay, thank you.
Thank you, guys. So let me stop the recording first.